we have done in the previous session. So if you remember, we talked about atomic radius, and I am sure now you very well remember that there are 4 types of atomic radius. What are they? Covalent radius, metallic radius, van der Waals radius, and ionic radius. I'm sure you know how to find it. Then we had a discussion about screening effect. We utilized it in understanding the size, and we also started small introduction to ionization energy, right? So let's take ionization energy forward and let's see what is waiting for you today. It's none other than ionization energy continued, and we are going to talk about another trend of electron gain enthalpy. So let's see what are we waiting for. If I ask you the general trend of ionization energy, I'm sure you know it very well. As we move along the period, what happens? As we move along the period, the size decreases, general trend. If size decreases, you know that. Why is it happening? Because effective nuclear charge, which is Z effective, increases. If Z effective increases, there is a strong hold of the nucleus to the outermost shell. Hence, it is difficult to remove an electron from the outermost shell. In that aspect, I'm sure you can understand, ionization energy increases along the period. What about down the group? As we go down the group, the size increases. So the last electron is kind of chilling and it is very easy to remove that electron. Hence, ionization energy generally decreases as we go down the group. So let's quickly recapitulate when we talk about all the factors one by one, layer by layer. So the first one is the size of the atom. You know that higher the size, easy it is for electron to be removed. So lower the ionization energy. Smaller the size, more is the nuclear hold, and hence difficult it is to remove an electron, right? So ionization energy increases. Size role you know. Let's see the next one. Nuclear charge. So nuclear charge, I'm sure, has a role to play in size also. So of course, it has a role to play in ionization energy also. And you know that when I talk about nuclear charge, higher the nuclear charge, more is the hold, more it doesn't want the electron to leave. And if more is it wanting electron not to leave, more the energy will be required to remove the electron, the outermost, most loosely bound electron when I'm talking about IE1. So if more energy is required, ionization energy is high. If Z effective is high, right? Next, you already know is screening effect. Higher the screening effect, lesser is the ionization energy. Screening effect is shown by the core electrons, the inner electrons, right? And higher is the screening effect, okay? Then they are protecting the last bencher electron from the nuclear hold, and hence ionization energy decreases because that very last bencher electron is chilling out in the outermost shell, right? And inner electrons are shielding the outermost electron, and hence it is easy to remove it. So screening effect, higher the screening effect, lesser the ionization energy. Easy it is to remove an electron. Okay. Next is, now you know, penetration effect. Higher the penetration effect, higher the ionization energy. All right. More is the penetration power, higher the ionization energy. Okay. And next rule is that of electronic configuration. So you would see that higher ionization energy for half-filled and completely filled electronic configurations, okay? So you will see that wherever some sort of anomaly, some sort of irregularity is coming, that would be coming because of half-filled or fully filled electronic configurations, all right? Now I want you to see a graph out here of the first 60 elements. And you will see that there are a lot of irregularities. The graph is not very gradual. The graph doesn't look like this, 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 this. It doesn't look like something gradual. We can see some sort of irregularities out here. But one thing which is certain out here is a thing of beauty, which is of the noble gases. Observe all the noble gases out here, right? And you know that as we are moving from helium to xenon, what is happening is, look at the ionization enthalpy, which I'm sure you know the energy which is required to remove an electron. For all these, you know that if I talk about the valence shell, the fully filled orbitals are present. So of course, very high energy is required. So the first point that I want you to analyze is all the noble gases has very, very high ionization energy. That's something that I want you to observe out here, right? Then second thing that I want you to observe is the group 1 of S block. So group 1, S block elements, group 1, you can clearly see that they are having low ionization energy. In fact, if I just connect the dots out here, what you can see is it is gradually decreasing as we are going down the group. In fact, cesium, you can observe, is having the lowest ionization energy. What does this suggest us? It suggests that cesium immediately gives an electron to become cesium plus. All right. So, in fact, the ionization energy is very, very low, and hence you will see a lot of applications of cesium at a lot of places. I'll talk about that. So, you can clearly see that as we are going down the group, the ionization energy is decreasing, but somewhere there are anomalies. So, let's just magnify this a little and understand in terms of questions, understand the trend in terms of the factors that we just talked about, right? So let me first pick up the ionization energy of second period elements. So when I'm talking about second period, that means we are talking about along the period, right? And if I'm talking about along the period, that means what? As we move along the period, Z effective increases, so ionization energy also increases, and now we can connect the dots that size decreases. Okay, but if we have this fair idea, so we know that second period means Li, Bi, Be, Knopf, Ni, right? So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. These are the second period elements. So, of course, the order is pretty simple, which I am sure looks something like this. Is it? You agree? What do you think? Do you agree? Give me a yes or a no. I just want yes or a no, not an explanation, nothing else. This is what, if we know the general trend, this is what we are going to answer. But we are smart and we have done the factors affecting ionization energy. And since we have done factors affecting ionization energy, we can't be fooled so easily. We know that here something strange is at play. It is not as simple as it sounds. There are exceptions, and the exception is this. Look at this, boron and beryllium. So beryllium and boron, this should have been, but here boron and beryllium is what we are observing. Similarly, nitrogen and oxygen and nitrogen is in the real answer, the right answer. Okay. So you can clearly see that in the right answer, this is one anomaly and this is the second one. Clearly, I'm sure The reason should strike the doors of your mind immediately, because today you have done many factors other than size, other than screening effect, other than the Z effective. You have today talked about penetration effect, and today we have also learned electronic configuration plays a major role. So here I'm sure that the moment you know beryllium, you have some electronic configuration striking your mind. And when I'm talking about nitrogen also, we have some electronic configuration striking our mind. So is electronic configuration the only factor playing a role? Let's see. So if I talk about the first one, which is boron and beryllium, I just told you about the electronic configuration. All right. So you can clearly see there is a fully filled orbitals which are present in beryllium, but something major is at play, which is the penetration power of 2s. Penetration power of 2s. You know that 2s is very close to the nucleus as compared to 2p, of course. So, what difference does that make? So, since it is very close, 2s electrons are very close to the nucleus, it is very difficult to remove those two electrons or that one electron from the 2s, and also it has fully filled electronic configuration. So we know that there has to be an anomaly coming up, right? Next, also we can predict very well oxygen and nitrogen. We know that there is some half-filled electronic configuration when we talk about nitrogen, which is 2p3. And since there is half-filled electronic configuration, there are high exchange energies. There is symmetry. So previous sessions should strike your mind, right? So exchange energy is high, symmetry is high. So hence nitrogen has more ionization energy than oxygen, right? So the trends should now keep coming in your mind. You should now connect the dots with the electronic configuration, with the penetration effect, with the size, with the Z effective. Everything in mind, okay? Also, let's see the whole IE1, IE2 and IE3 idea. You should know that IE1 is greater than, IE1 is less than IE2 and IE2 is less than IE3. Maximum should be IE3. So let's see the point to be noted out here when I'm giving you the data for the successive ionization energies or enthalpies. So everybody, come on. I want the focus here. Let's observe the table and let's draw some conclusions. Okay? First conclusion, please see. We are here talking about second period. Right? Second period elements are given. If I ask you the first thing first, the order of IE, can you clearly see that the order of IE is IE3 for any element you pick? Any element you pick. Let me pick carbon. 461823531086. Any element you pick, for a matter of fact, you can see that everywhere IE3 is greater than IE2 is greater than IE1 without an exception. Without an exception. The difference might be very great or might be less, but we can come to this conclusion that IE3 is greater than IE2 is further greater than IE1. Okay? So, this is first conclusion. Second conclusion, we can see IE1 now. Okay? And we can see IE2 now. And we can see IE3 now. We know the general valence shell electronic configuration is NS1. So we know that the moment it gives its outermost electron, it attains the noble gas configuration. If it attains a noble gas configuration, means that to remove the next electron, first electron removal is pretty easy, but the removal of next electron will become very, very difficult. Right? So you can see that lithium has a very, very less ionization energy. The last electron can easily be removed because we are getting a noble gas configuration. Right? So wherever the removal of electron leads to the formation of noble gas configuration or half-filled electronic configuration, removal of that electron becomes easy because on the removal of that electron, what we are retaining is even stable electronic configuration. So second conclusion will be even more clear when I give you the data for all the first group elements. But from here we can see lithium has very low ionization enthalpy. Also, if you see, first ionization enthalpy for lithium is low, but second is very, very high. And then third one, you can see, has to be higher than the previous one. But if you talk about the difference, you can very well see that removal of the next electron. First electron is easy, but second electron removal in lithium is very difficult. Let's see the trend when we are getting, let's come to boron, okay? Removal of first electron is again easy, okay? But second electron, of course, is taking more energy rather. Why? Because on removal of 2p, 1 electron, what we are getting is a very stable electronic configuration. Also, let's see, we know that here if we are going to remove 1 electron, okay? Here if we are going to remove an electron, it will lead to stable electronic configuration 2p3. But removal of another electron from 2p3 is very difficult. So wherever you see half-filled and fully filled electronic configurations, it is becoming very difficult for us to remove an electron. Okay, so these are the conclusions, which are very minute conclusions that I've just drawn. Please have a conversation with yourself when you see this kind of a data. Ask yourself as many questions as possible, that why is this happening? Why is that happening? And if you're not able to answer, please question us. Ask from us. Okay? So this is the wider view that I have given you about the successive ionization enthalpies data. But we must know how to utilize this data. So let's see certain questions of utilization of this data, because it is very important. The whole data will help you a long way in deciding which group in a while, okay? So let's utilize the data and let's see certain questions. The question coming your way is the first ionization potential of sodium, magnesium, aluminium, and silicon are in the order, right? So can we see that if I just arrange them, they are all third period element? Okay, so let's see the elements in discussion. We have sodium, magnesium, aluminium, and silicon. So they are third period element. That's the first thing that you can see. Also, they are lying in one single period. So we have to talk about along the period. So if I talk about along the period, we know the general trend that sodium should have minimum and silicon should have maximum, because as we move along the period, the ionization energy increases. But we also know for a fact that the moment I am talking about magnesium, the electronic configuration is very important here. 1s2, 2s2, 2p6, 3s2. Why 3s2? You know now how to write the electronic configuration. The atomic number is 12 for magnesium. So you can clearly see fully filled electronic configuration coming your way, right? The moment you see it, so of course it should have greater ionization in the energy as compared to aluminium. So this should be the order. So the thing that I can write it is like this, right? Or I can write it like this. Any of the ways I can write. So the right answer is option A. All right. Okay, let's see this question, which says the element which has highest second ionization energy. So first is not asked, if first would have been asked, I'm sure that it would have been very easy. The noble gases has the highest ionization energies. And why so? When you can see that we have sodium, magnesium, calcium, they are metal category. And metals would love to become cations. Metal loves giving their electron to become positively charged species. But noble gases are very, very stable. They have stable electronic configurations. And everybody else wants to become noble gas configuration. So why would noble gas configuration, which is a noble gas, would want to become anything else, right? So right here, we have this question wherein the first ionization energy question would have been very easy. It should have been argon, but for understanding sake, let's write down the electronic configurations for all, for sodium, for magnesium, for calcium, and for the last one is argon. 11, 12, 20, 18. Let me write down the electronic configurations. 1s2, 2s2, 2p6, 3s1. 1s2, 2s2, 2p6, 3s2. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. 1s2, 2s2, 2p6, 3s2, 3p6. Clearly, you can see many stable electronic configurations which has fully filled orbitals, but yet argon is going to exceed anybody else because it's a noble gas. Highest ionization energy, one will be of argon as an element. But let's say that anyhow we have to remove one electron. Let's remove one electron, which is called IE1, which means that removal of one electron, okay? So when we make all of them as unipositive ion, what we are going to get is the valence shell electronic configuration here will be 2s2, 2p6. Okay, 3s0. Then we have for the other one, we will have 3s1. Then for the other one, we will have 4s1. And for the other one, we will have 3p5. Clearly, you can see that if I ask you after removal of one electron which becomes extra stable, it is none other than sodium which becomes extra stable because of the noble gas configuration it has achieved, right? It is neon's electronic configuration that you can see which sodium has achieved after removing one electron from its valence shell. So we have the right answer as option A, of course, right? Because it is having a noble gas electronic configuration now, and removal of electron will be very, very difficult, not just because of the fully filled orbitals, but also because of the high penetration of 2p, right? Another question. The screening effect of inner electrons on the nucleus causes screening effect. The question is from the screening effect of inner electron. The outer electron is here. These are the inner or core electrons. The screening effect of the inner electrons on the nucleus causes a decrease in ionization energy, an increase in ionization energy, no effect in ionization energy, an increase in the attraction of nucleus on the outermost electron. So when Rahul has good friends in front of him, bunking the class from the last bench becomes very easy. Hence, ionization energy decreases if the inner electrons are shielding well. So screening effect of inner electrons decreases the ionization energy. Why are we talking about ionization energy decrease here? Because it is always of the most loosely bound electron, right? Which is the outer one, which can easily chill and go, right? This was pretty simple. So now I'm sure that the idea of ionization energy is becoming very, very clear. What is ionization energy? You know. Factors affecting ionization energy, you know. You now know very well that IE3 is greater than IE2 is greater than IE1 always. And you can also now, with great sense of understanding of electronic configuration, think how important the electronic configuration is for deciding the ionization energy and also the group. So now is the next one, which is the topic of discussion, that if ionization energy is given, can you find the group, right? So this is very interesting. How to find group of an element if successive IE is given. All right. So you can see that for lithium, sodium and potassium, that means the same group. Group is same and IE1, IE2, IE3 is given. How should we see this whole data? How should we realize that though we know right here that it belongs to group 1, but how do we actually come to this conclusion with certainty? Let's say I hide this. Don't see it. Close your eyes. Okay? I'm calling it X, Y, and Z. Right? How do you have to get to know which group it is? So right here, now that you know it is group 1 because you saw already, right? So you've done a little bit cheating here, but don't worry. Questions coming your way. I will test out of you whether you got it or not. But how to see first, let's get that idea right. So if you see, first IE is very low. First IE is very low. Look at this. Idea 2 is second IE is very, very high. Why am I saying very, very high? Look at the difference. No. Look at the difference. 520 into like not even 10 times. More than that. Around 14 times is going to give me this result. So more than 10 times is the IE2 as compared to IE1. And we know that IE3 has to be greater than IE2, which is in turn greater than IE1. This we know, but we can observe from here that IE2 is coming out to be exceptionally more. The difference between IE1 and IE2 is exceptionally more as compared to IE2 and IE3, which is bound to happen, right? That means that must be, if I talk about valence shell electronic configuration, NS1 would want to remove an electron to become noble gas electronic configuration, right? So in that case, if that is happening, please understand we are attaining noble gas configuration, or we are attaining fully filled orbitals, right? In that case, removal of another electron is certainly going to be very difficult. Hence, this giving us a proof that this is a group 1. Similarly, let's say IE1 is okayish high, IE2 is very, very okayish high, because IE2 has to be greater than IE1, but IE3 is exceptionally high, right? In that case, you can confirm that it's group 2. Let's say the first IE is extraordinary high. Then you know that it is for noble gases general. See, the idea of examiner is to check your common sense, not check how much you can cram. Before I give you more questions of deciding the group, I want you to keep some points in your mind. The points to remember is, number 1, non-metals will have higher values of IE1, IE2 and IE3 compared to the metals. And of course, IE3 for anything will be greater than IE2, which will be greater than IE1. This is a common thing that we have drawn a conclusion of. And non-metals will have higher IE1 as compared to the IE1 of metals. Metals would love to give their electron and become positive. Alkaline earth metal and pnictogens have higher values of IE1 as compared to the succeeding group, the next group, okay? Up to 4th period, point to be noted, because after that, you know that more D and F electrons are going to enter. They're certainly going to do some notorious activity for sure. So, here we know that we have valence shell electronic configuration as ns2, and here we have np3. So half filled and fully filled role is also clear. Third is IE3 of alkaline earth metals show exceptional jump because ns2 now has become ns0, and we have n minus 1 p, let's say. So I'm not talking about when d orbitals are coming into picture just before s. Okay, so in that case, again, we know this is something that we are going to observe, an exceptional jump. Noble gases have highest IE1 in any period, okay? Question now coming your way. IE1 and IE2 data is given to you for 3 elements A, B, C. Which one of the following is likely to be a non-metal, is likely to be an alkali metal, is likely to be an alkaline earth metal? Okay, so they've not asked noble gas. You know that the highest one should have been of noble gas by the virtue of it being noble gas. Non-metal, that means that IE2, IE1, of course, has to be highest. Okay, so for non-metal, IE1 has to be highest. IE1 is highest of C, so I can fairly say that it is a non-metal. For alkaline earth metal, we know that what is the very idea that we know that IE1 of group 1 is lower as compared to the IE1 of group 2. So this is group 1, this is group 2. Okay, so from that matter of knowledge that we know, I should call this as alkali and this as alkaline earth. But let me check whether I'm right or wrong, because I know that NS1, if one electron is removed, we get NS0 as the valence shell electronic configuration, and removal of an electron further from the inner shells is going to be very, very difficult. So the IE2 for the alkali should be very high. Clearly, it's very high, right? You can clearly see that IE2 is very high. Here, IE2 is not very high. It's just the double. But here, it is not double. It is more than that. So clearly, you can see that. Bingo, right? Okay, next one. The first 4 ionization energy values of an element are given to you. All right, they are given in kilocalorie per mole. The number of valence electrons in the elements is R. Number of valence electrons. All right, so that's interesting. Let's see whether you get it right. Clearly, observe that we have 191, 578, 872, IE1, IE2, IE3. Means removal of first electron, second electron, third electron is pretty simple. But it is taking huge amount of energy to remove the fourth electron, isn't it? To remove the first electron. So from a species, let's say M, IE1 M plus we are getting. The energy, let's say, required is 191, pretty less. For M plus 2 or M2 plus, the energy required is 578. From M2 plus to M3 plus, the energy required is 872. Pretty decent. We know that IE3 has to be greater than IE2. But IE4, it's exceptionally high. It's some bomb high, no? 5962, it's crazily high. So M4 plus is certainly taking some toll, and hence we can fairly say that the valence electrons would be 3, because removal of those 3 electrons were pretty easy, but removal of fourth electron is pretty difficult. So valence electrons must would be 3, right? So this is how the questions can be asked. Okay, so also you can see that any of the elements which has the ability to give an electron very easily, we say it has low ionization energy. And if there is an element with the low ionization energy, we know that it can become cation. It can become positively charged ion. And if it can become positively charged ion, we see that in a reaction, they are metals who becomes positively charged ions. So we relate any element which has an ability to give an electron easily are metals. This is how we define. So can we set a link between ionization energy and metallic character? We should be able to. So let's see. So metallic character refers to the level of reactivity of a metal. Metals tend to lose electrons in a chemical reaction. So which is a better metal? Which gives electron easily. They are the donators. They love giving their electrons and attain noble gas electronic configuration. All right. So they give electrons, and whichever gives electron easily will be a better metal. Easily, if some element is able to give an electron, lower is the ionization energy. Hence, you know that if I talk about metallic character, it follows the rule that as we move along the period, ionization energy increases. So metallic character decreases. But as we move down the group, we know that size increases, ionization energy decreases, and metallic character increases. So we can well establish the link between the metallic character, the ability of an element to become positively charged ion. Easily it is able to lose an electron, better a metal it is. So metallic character and ionization energy we can now understand. But how about non-metallic character? Is it as simple as that? Let's see. Let's not be in a haste. When I'm saying non-metallic, you will see that they generally accept electron. So non-metallic character relates the tendency of an element to accept electron during a chemical reaction, unlike metals which had the ability to donate electrons or give electrons at the time of the reaction. Okay? So, here, let's not be in a haste to simply judge non-metallic character on the basis of ionization energy. Let's understand the ability to gain electron and to understand the ability to accept electron. This accept term is very important. To accept electron, we need to understand electron gain enthalpy. So what is this electron gain enthalpy? Let's understand. And if I give you the definition of electron gain enthalpy, what happens is when an electron is added to a neutral gaseous atom to convert it into negative ion, the enthalpy change accompanying the process is defined as electron gain enthalpy. I'm sure you're getting a nostalgia of ionization energy, wherein what we were doing is the energy which was required. So let's draw parallel between the two and try to understand ionization energy and electron gain enthalpy. So there the term that I used was energy which is required. All right, so delta H is positive. That means we are giving energy. Energy has to be supplied to remove the electron. But here we are using a very fancy term, energy change. The associated energy change or energy change accompanying the process. So basically, electron gain enthalpy can be negative also or positive also. So we can't say it is always negative or positive. It can be positive or negative. So it's the energy change, we can say so. In ionization energy, what we were making was, can I say we were making a cation, a positively charged anion, positively charged ion. In electron gain enthalpy, we have to make negative ion. That means anion. So negative ion and cation, positive ion we are making in ionization energy because we are removing an electron. In electron gain enthalpy, we are giving an electron, hence we are making an anion. Also, you remember in ionization energy also the same term came, this neutral gaseous atom or isolated gaseous atom. You remember? Because we do not want addition of various energies together. Here also the same term has been used, the isolated gaseous atom, or you can say neutral gaseous atom. This is a similar term coming because no association we want of any other energy with the particular energy that we are talking about. So there is this also very important difference, that what we are getting is ionization energy, we are getting a cation. Electron gain enthalpy, we are getting an anion. And ionization energy, we have to always give energy. Electron gain enthalpy, we may have to give energy, or energy might also get released by itself. Okay, now keeping the parallel in mind, let's understand electron gain enthalpy further. So here you can easily write it like this. The electron is removed. Whereas here what we know is electron is added. Okay. So hence we can have positive as well as negative electron gain enthalpy. When energy is supplied, like I told you, is positive electron gain enthalpy. When energy is released, okay, delta H here is positive, energy has to be given, all right, whereas here energy is released, delta H is negative. All right, so keep that in mind, and let's understand electron gain enthalpy with a good example. Let's have a look at this case out here. Everyone, be with me and listen to the story. There is this old guy out here, all right, old man out here, who has just had his meal. He's just done with his chapati and dal. And he is full. His appetite is satiated. Of course, he's in his old age and the temptations doesn't lure him enough. And on the other hand, we have this chap out here. He's a BYJU'S student. And after classes, BYJU'S classes, one after the other, he's very tired and he's very, very hungry. He has used his mind too much. And when you utilize your mind too much, you feel hungry. So he is hungry. The guy, the BYJU'S student out here. Okay. Now mother gives cake to both, to the old man and to the BYJU chap out here. Okay, the old man, of course, is in his old age, is already full, is satiated, is not hungry, but mother wants him to eat. Mother is like, no, you have to eat. Old man says, I am done. No, I can't have. But maybe his daughter-in-law is like, after his life, no, I made it with such hard work, you have to eat. Old chap says, no, I can't have. She's like, I will leave home if you don't eat. Please, you would have to eat. I have spent so much time. I have made so much efforts. You have to eat. What I mean to say, she's applying a lot of energy for the old man to eat the cake. On the other hand, we had this BYJU'S student out here who has just attended his sessions one after the other, and he's super hungry, and mother would not have to say a word. She just has to keep the cake on the table, and this guy out here will just munch it without even mother asking him to do so, because he's hungry. So in one case, energy has to be given for him to eat, and in the other case, energy is released. He automatically has it, and he feels stable, he feels good, he feels satiated, his appetite is quenched. Okay. Now what? Let's say the old man had the cake and he is in his old age, we must realize. There are chances that he might vomit after it, not because the daughter-in-law made it bad or something. She's not added any bad salt inside, but let's get that thing right, that he is, let's say, in his old age and the cake doesn't suit him and he vomits. So there is a repulsion that happens when you were not willing to eat something, yet you give it by force, and then what is happening? His stability has gone down. On the other hand, this BYJU'S chap out here, he was hungry, he had food, he's relaxed, he feels stable. Okay, so let's now draw a parallel with the electron gain enthalpies example that I've just given you. So I just told you that what we are doing is we are giving an atom an electron and we are making it negative. So we can have positive electron gain enthalpy and negative electron gain enthalpy. Let's understand both one by one. So if I talk in case of positive electron gain enthalpy, energy needs to be spent, and hence enthalpy delta H. How do we write it? Delta H, which we write for enthalpy change or energy change, delta H, Eg, written as a subscript just below this triangle. Okay, we write this Eg, which stands for electron gain. So delta H is positive in, as the name suggests, right? Whereas negative in case of negative electron gain enthalpy. The first is pretty simple. Next one is the atom is reluctant for the addition of the new electron in its valence shell, and this drives it towards instability. Remember the old uncle? He did not want to have the cake. If you force him to have it, instability. Whereas the BYJU'S chap out there, the atom, in order to gain stability, tends to gain electrons. So he is gaining energy, he's gaining stability, I should say, and hence you can very well say that he would therefore gain or have that cake to gain stability. So here in negative electron gain enthalpy, if energy is being released, of course it is happening because it is driving the atom towards stability. Next is very important point coming your way. Noble gases and alkaline earth metal have high positive electron gain enthalpy. Can you tell me why? Noble gases, they're like the old man. They're already full. They're satiated. They already have noble gas electronic configuration. The orbitals are already fully occupied. So, of course, they would not want another electron to come. They would not want any sort of repulsion. They're happy amongst themselves. So is with the alkaline earth metal. Ns2 is the valence shell electronic configuration, you remember now. And hence, already they are also very much satiated. So group 2 and group 18 will have positive electron gain enthalpy. Whereas halogens have very high negative electron gain enthalpy. They are like very hungry. Sometimes some of the teachers refers group 17 as politicians also. Can you guess why? I'm sure. Homework, okay? Think about it. So let's understand factors affecting electron gain enthalpy. So when I talk about the factors, atomic size, you can see Z effective and screening effect. Let's see the fusion between the four. When I talk about, let's say, an atom, which has a very big size. Okay. So size is big. I can say because Z effective is low, because I can say that the shielding of the inner electrons was high. If shielding is high, right? If shielding would have been less, the hold of the nucleus to the outermost electron would have been high. But if shielding is more, we can say that the size is hence high and Z effective is hence low. We know this relation. But what will be the impact of these three things on electron gain enthalpy? So let's say to this atom, we are willing to give an electron to this atom, and we want electron to come from infinity to its outer shell. In order to give it electron, when the size is big, we can say that less energy will be released. Okay, less energy will be released because nuclear force of attraction, which is, let's say, some positive attraction to the negative electron, is not there, is very less. So energy released will be very less. Okay, so electron gain enthalpy will be less if the size is more, if Z effective is less, and if shielding is more. So if I see the relation between size and electron gain enthalpy, can you see inverse relation? Yes, there is inversely proportionality that you can see here. Similarly, Z effective is less, electron gain enthalpy, the magnitude of electron gain enthalpy is less. We can see the direct proportionality here. And here you can see that shielding is more, so electron gain enthalpy's magnitude is less. So is what you can see here, the inverse proportionality. So these are the three factors which I'm sure you can easily understand. Smaller the atom, the nuclear force of attraction is very high. So you can understand this positive attraction is very high towards any negative electron, and hence electron gain enthalpy, the magnitude of electron gain enthalpy will be high. Okay, so more energy will be released. Now let's understand electron gain enthalpy layer by layer with few points which I want you to keep in mind. The trend of it. All right, so in general, if I talk about electron gain enthalpy, becomes more negative in going from left to right. We know that if we go from left to right, the Z effective increases and the size decreases. So we just saw that if the Z effective increases, it wants to attract an electron, it wants an electron, and hence the electron gain enthalpy should be high, more negative. The magnitude of electron gain enthalpy should be high. That means more energy should be released. We know that group 17 loves to accept an electron out of the whole periodic table. So they are more negative in going from left to right in a period, while it becomes less negative in going from top to bottom. Top to bottom, size increases, and we know that the magnitude of the electron gain enthalpy also decreases. Less energy is released as we go down the group. General trend. Okay, so however, the variation does not show a perfectly regular trend. Like always, a period or a group with a number of exceptions there are. Let's see further. Electron gain enthalpy across the group as we go from left to right. You know that it becomes more negative, and this is because of Z effective. And you can also understand how easy or difficult it is to add an electron. If more energy is released, it is easy to add an electron. If less energy is released, it is less easy to add an electron. If energy has to be given, it is very, very difficult to add an electron. So this idea is clear. Also, you know that from top to bottom, how we can relate it to size. Higher the size, less is the Z effective, and hence the energy released will be less. So the magnitude of electron gain enthalpy will be less, right? So the general trend is something like this. Okay, the general trend looks something like this. Left to right, what happens? And from top to below, what happens? So electron gain enthalpy increases along the period and decreases down the group, the general trend. Okay. But if I talk about the positive electron gain enthalpy, these are the ones that should knock the doors of your mind. Inert gas elements, when I talk about, you know that when I'm talking about inert gas, they have noble gas electronic configuration. They do not want electron. They are satiated. Alkaline earth metal, valence shell electronic configuration is ns2, fully filled orbitals are there. And nitrogen, half-filled electronic configuration is there for nitrogen. Why only nitrogen? Why not other phosphorus or other elements of nitrogen family? So please remember the size is also playing a major role, right? So as we are going down the group, the size is increasing. So keep that in mind, right? So let's see successive electron gain enthalpy. What is successive? Like you have seen in ionization enthalpy, you removed one electron, then you removed another electron, then you removed another electron. Okay, so you remember there IE3 was always greater than IE2, which is greater than IE1. But that was always positive. Here, we know that electron gain enthalpy can be positive or negative. The positive examples are now clear: inert gas, alkaline earth metal, nitrogen. Negative ones are most of them. So one electron addition is simple. And if, let's say, after addition of one electron, we are trying to add another electron, that is not going to be easy, because what is going to happen is electron repulsion is going to outweigh the nuclear forces of attraction. Even though, mind you, even though after attainment of an electron, the atom is gaining so much stability that it is becoming noble gas configuration, let's say. Because we say no, we claim that noble gas configuration makes an atom stable. Look at this oxygen, O minus, all right, already a uni-negative ion is accepting an electron to become O2 minus, which means 10 electrons now, 1s2, 2s2, 2p6. The electronic configuration of neon, which you see right here. Okay, so noble gas configuration coming, no? So it should have been readily done. Rather, energy should have been extravagantly released because you are celebrating your becoming of noble gas. But that is not happening, mind you. Energy has to be given. So make sure you highlight this point, that electron gain enthalpy, second electron gain enthalpy, or any further successive electron gain enthalpy will be always positive. The first electron gain enthalpy, let's say if it is negative, the second one will still be positive. If second is positive, third will automatically be positive, and more positive rather. Right? So get this picture right, and now I'm going to take you through some very important questions, guaranteedly from where the question is asked. Okay, I'm giving you 90% probability here. Let's see what are these questions. First one from electron gain enthalpy is, what should be the order of magnitude of electron gain enthalpy for halogens? Halogens means group 17. Group 17 means we go along the period or down the group. Of course, group 17, down the group we go. And since we go down the group, the size increases. Size increases. We know electron gain enthalpy magnitude decreases. And if the electron gain enthalpy magnitude decreases, this should be the order. Isn't it? hold on to your emotions because this is wrong. The right picture is this. Okay? So why is this kind of a change happening? Is very simple because of fluorine and oxygen. I'm going to tell you about oxygen in a while. Let's just hide it, okay? Pretend you have not seen it. Fluorine has a very small size. Fluorine has a small size, so what happens is there is a very limited space. In that limited space, you are making more electrons come. So more electronic repulsion, even though Z effective should have been high, but here the electron repulsion outweighs. Okay, so in case of fluorine, valence shell electronic configuration is 2s2 2p5. On adding another electron externally to the valence shell, it causes severe electron repulsion, due to which the system becomes comparatively unstable. Okay, that happens in the case of oxygen also. So I'm sure if I ask you for chalcogens, can you guess the order? Chalcogens means group 16. So as we go down the group, same trend should have been followed. But again, this is not so. So here, please observe that this is a wrong order. The right is here. In fact, I want you to see that it comes at end. Okay, oxygen is coming at end here. Please observe the two trends. They are exceptions, and hence I want you to observe it very carefully. Here chlorine and then fluorine. Fluorine is going to second number here. Chlorine and then fluorine, then bromine, then iodine. So fluorine would still like to accept an electron even if there was electronic repulsions. But with oxygen, the energy is lesser than any of the other group 16 elements, right? Look at this. It is going at the end. All right, so point to be noted. This should be kept in your mind. All right, so why such exceptions? I'm sure it is quite clear that chlorine and sulfur are having larger size. They belong to third period. Whereas if I talk about the fluorine atom or oxygen atom, they belong to second period, small size. So their order is quite different from the actual order, and chlorine has the highest negative electron gain enthalpy in the entire periodic table. Cool? So remember that. So electron affinity now is something that I can easily introduce along with what we have just talked, electron gain enthalpy, because electron affinity is very similar to negative electron gain enthalpy. All right, roughly we can say that the negative electron gain enthalpy, if you take the magnitude of it, we get electron affinity. That means the scale for electron affinity will start with 0 only. There is no negative scale out here. So more is the energy released when an electron is gained by an atom. Higher is the electron affinity. Affinity means maybe love to an electron. All right, inclination to an electron. So electron affinity, higher the electron affinity means higher is the tendency to accept an electron. Lower the electron affinity means the electron affinity, of course, electron does not want to get added or wants to get added, but releases less amount of energy So what about the ones which had positive electron gain enthalpy? For them, we take electron affinity as 0 simply. So it is defined as the energy released when an electron is added to a neutral isolated gaseous atom. So electron affinity is deciding the delta H value automatically by saying that energy is released. All right, so that means negative electron gain enthalpy. That means delta H is negative. Okay, so same thing, everything is same, just take electron affinity as the negative electron gain enthalpy. Generally, order of electron affinity will be negative of the electron gain enthalpy, whereas the order of electron gain enthalpy will be opposite to EA, of course. Difference between electron affinity and electron gain enthalpy is out here. All right, so electron gain enthalpy or electron affinity, when I am talking about, okay, in oxygen family, the electron affinity order, sulfur is most and oxygen is at last, but order of electron gain enthalpy will be reverse of it. Oxygen is first and sulfur is least. What is this meaning? Let's understand. What was here came here. 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 Because we are talking about electron affinity, we know that sulfur wants to accept an electron, and in oxygen there is electron-electron repulsion coming in, so it doesn't want to accept electron. I can say that. But when I'm saying electron gain enthalpy without saying negative electron gain enthalpy, that means that for oxygen, let's say if the energy released was very less, minus 141, and for sulfur minus 200, then for selenium minus 195, then minus 190, then minus 180. Clearly oxygen is minus 141. So if I include the sign, I will say the maximum electron gain enthalpy is of oxygen. But if I take the magnitude of the electron gain enthalpy, all right, and not include the sign, polonium, the sulfur, let's take the magnitude, okay? Can you clearly see? This is what I have taken as a magnitude of whatever electron gain enthalpy was given. This is electron affinity roughly, or negative, the mod of the electron gain enthalpy, okay? So this is, now you can see the maximum for sulfur, then we have selenium, then we have tellurium, then we have polonium, then we have oxygen. Sorted. Clear? So formation of F minus is exothermic, but formation of O2 minus is endothermic. Why? Of course, first electron gain enthalpy. This is going to be second electron gain enthalpy. Super easy. So ionization energy is clear. Electron gain enthalpy positive and negative is clear. Electron affinity, which is nothing but the negative electron gain enthalpy, is also clear. Okay, so remember that second and subsequent electron gain enthalpies are going to be always positive, the takeaway. Next question coming your way. In comparison with alkali metals, the electron affinity of halogens is electron affinity. They love electrons. All right? They love electrons, like politicians love money. Group 17 or halogens loves electrons. So I can say very high. All right? Next one. Which of these elements has the maximum electron affinity? Maximum, of course, out of these. Answer. Don't see the screen. Everybody. So, of course, sodium, which is a metal, magnesium, which is a metal, aluminium, which is also a metal, and we have sulfur, which is a non-metal, and non-metals generally have higher tendency of accepting an electron, and hence for sulfur we have seen that in group 16 it was leading, and out of these people out also It is leading, right? Next one, the electron affinity of carbon is greater than oxygen? No. Oxygen likes to accept an electron more than carbon. Why? Because as we move along the period, the electron affinity increases. Sulfur is less than oxygen? No way. Sulfur was a leading showstopper of group 16. Iodine is greater than bromine. Bromine was greater than iodine. As we go down the group, the electron affinity decreases. Bromine is less than chlorine. Chlorine had maximum, right? And not just maximum, electron affinity of chlorine is highest in the whole periodic table. So the right answer is D.